to today's webinar, the most important questions not being asked in statistical research. I'm William Bannon of Stats Whisperer. I'd like to thank you very much for attending this webinar. To me, this is the most important webinar we've done so far because these questions really represent the cracks in the foundation of quantitative research worldwide. So I'd like to thank you so much for taking this webinar, and I hope you get a lot out of it. So, just what are the most important questions not being asked in statistical research today? Well, they have to do with checks of data integrity. Have all necessary checks of data integrity been considered within a quantitative study? They're the most important questions because not making these checks could easily, very easily, result in inaccurate statistical findings. So we have to ask ourselves, what is the value of a study if the findings are incorrect, right? So that sounds logical, right? Which adds to our case of why these checks should be done. So what we're going to do in this webinar is first briefly discuss what these checks of data integrity are, right? So if they're so important, just what are they, and how do we meet them? So there are 4 general areas that we identify as checks of data integrity. Now, these are 4 areas that I've specified, so that it's not a standard by the field. And so this is just a way to help us conceptualize just what are checks of data integrity. So we'll be reviewing the first one, statistical power. The second one, test assumptions. The third one's missing data. And then the fourth one is measurement tools. And we're going to illustrate how each can distort findings, right? So if each isn't done properly, how can findings be compromised? So in essence, what we're doing is we're building our case. So we're saying that these are really important, they need to be done, and we just can't say that. We need evidence, right? We need to build a case of why it's so important to do these checks. So when we recommend to other people, or to ourselves, right, that this really needs to be done, it should never be neglected, we need evidence behind our statement that will support it. And in building our case, we're going to illustrate how just not checking one of these checks properly could result in incorrect findings. And we're not going to address today how not checking multiple areas could interact to really compromise findings. Then we're going to look at the prominence of the problem. The problem being, of course, that checks of data integrity are not adhered to as often as we might like. We're going to select a random sample of 20 peer-reviewed research articles, quantitative research articles, and assess them in terms of how these 4 areas of data integrity were assessed. We're going to be looking at 5 articles from nursing journals, 5 articles from social work journals, 5 articles from psychology journals, and 5 articles from medical journals. And to be fair, I should state up front, the articles I've selected are among the most rigorous out there by some of the most prominent people in the field. So they're really good articles. So even in really good articles, right, so we're going to give us every possible benefit to find evidence of checks of data integrity being made, so we're going to find the best articles out there. And then, of course, we're going to cross-reference them across the 4 fields, right? Not to not to create any sort of competition between the fields, right? But just to, just to get a more diverse sample. Then we are going to present possible solutions to promote a wider implementation of checks of data integrity. Pardon me. So we're going to suggest a standard model of data analysis, which is the 7 steps of data analysis model, and we'll discuss how that could promote a wider implementation of checks of data integrity. That will be in part 2. That won't be in this section. So to really look at how checks of data integrity impact findings, we should illustrate it rather than just talk about it. Right? So application is the best illustration. So we'll take a study research question, such as do levels of happiness differ significantly by age, income, or gender, or gender. So happiness is our dependent variable, and what we want to know is the dependent variable happiness significantly related to age? Is it significantly related to income? And is it significantly related to gender? It's a fair, straightforward, direct effects research question. Then we're going to illustrate, if this was our research question, how can mischecks of data integrity impact our findings? So if this is our research question and we're applying statistical tests to indicate if these relationships exist, how could skipping checks of data integrity compromise our findings? So here's our evidence. So we're going to illustrate how skipping the checks of data integrity could easily compromise our findings relative to this research question. Okay, so the research question in diagram form. On the left, we have our predictor variables, and on the right, our dependent variable. So on the left, on the top, the first predictor variable is age significantly related to happiness. The second box is income significantly related to happiness, and the third box is gender significantly related to happiness. Now notice we have a very simple model to test here. It's cross-sectional, one time point. It's not pre-post. There's not a terribly large amount of predictors. We have a few predictors and one dependent variable. And we're testing a very simple model. We're testing a simple model because the more simple the model, the more easily we can see how the checks of data integrity affect our results. So next, we will apply the 4 checks of data integrity to our research question. Now the first check, statistical power. Statistical power is often described as the power to reject a null hypothesis when it is false. The null hypothesis, stating that, for example, there is no relationship between age and happiness, or gender and happiness, or income and happiness. Right? In other words, it's our power also, reflexively, to accept a true study hypothesis. So typically, we would use the procedure known as a power analysis to calculate the minimum sample size required to detect a relationship between variables. So how do we know if we have enough people to test our research question? Do we need 2? Do we need 200? Do we need 2,000? We conduct our power analysis, and that will tell us. And if we have less than a minimum sample, the research question cannot be adequately answered. So in other words, we need enough people to test our research question, or else we can't answer it adequately. So we need the sample adequate, right? So effect sizes. So the effect size is the magnitude of the relationship between variables. So what's the magnitude of the impact income, the predictor income has, upon happiness? Right? Is it a small effect, a medium effect, a large effect? Right? How big is that effect size, for example? And the same with gender and age and happiness, right? What effect do each of these predictors have in determining the dependent variable happiness? Is it small, medium, or large? Well, if you're testing for a small effect, you need a bigger sample. Okay? So the smaller the effect you're looking for, so if we think gender has a small effect on happiness, we need a large sample to pick up that small effect between gender and happiness. So, and then of course medium and then large, right? So to get a large effect, to examine a large effect, that's the smaller sample. So in other words, we need at least a sample adequate to detect a large effect size. Right? So if our sample is so small that we can't even detect a large effect size between, per se, income and happiness, then our analysis really can't pick up. So the relationship might be there, we just can't see it. Right? So if we don't have enough statistical power, we're fundamentally statistically blind in picking up that relationship. So again, we need at least a big enough sample to detect a large effect size. So for example, consider we are using a t-test to examine the relationship between gender and happiness. Right? So here's our first inferential test where we'll look at how statistical power could impact the results. So are the results due to the actual relationship between the variables, or are they due to some error in the statistical analysis? That's what we want to know. So the t-test, looking at if happiness, right, the mean level of happiness measured on a scale of 1 to 5 is significantly different among males relative to females. So if we do a power analysis using the G-Power software, which is a free power analysis software available online, G-Power tells us if we set power at 0.8 and alpha at 0.05 and look for a large effect size, right, those are the standard settings, where power, you have to set power and alpha for power analysis. You need a power of at least 0.8 and alpha usually 0.05. So G-Power says to detect a large effect size between gender and happiness, we need at least 52 study participants. So that's saying we need 52 to pick up a large effect size. If there's a small or medium effect size, we won't see it because we won't have enough people even if we have 52. So consider this. How often have you seen a study that may have 40 study participants, right? Or even 50, because we need at least 52. 40 or 50 study participants, and it's using a t-test to examine the relationship between the independent and dependent variable. So here, we may have a t-test examining the relationship between gender and happiness, and it comes out to be not statistically significant. And so this is something commonly seen in the literature. We have a study. We have 40 study participants. A t-test is done, and there's no significant relationship between the independent and dependent variable, right? So this looks like an honest finding, right? But it may not be an honest finding because we don't have enough statistical power to pick up on that relationship between the independent and dependent variable. So if it comes out to be not statistically significant, that's not necessarily the case. The case may be we just didn't have enough people to illustrate the significant relationship that actually is there, right? We didn't have the statistical power to pick up on that relationship. So we make a statement that there is no relationship, but that's not appropriate because we don't have enough people to illustrate that. Pardon me. So what we're saying is the finding may be significant, but not with 40 people, right? Because you can't detect the significant finding. So the result is not a true finding. The results are not true findings, but are rather inconclusive. However, it's usually not stated that way in a research article. So to get something published, if you say the results were entirely inconclusive statistically. Right? So the thing is with only 40 people, we don't have enough study participants to say either way, whether there was or wasn't a significant relationship. Now you take the same t-test, and you have 52 study participants, and let's say there is a large effect size between gender and happiness. Well, with 52 study participants, just adding 12, right, if the trend is the same with the other 40, right, then now you can see the statistically significant relationship, right, because we have enough power to illustrate the existence of that relationship. Now here's our big question. How many small samples, studies of small samples, present findings like this, say with 40 or 50 people, as true findings, when the study is too underpowered statistically to indicate a conclusion in either direction? And even more important, how many times do people read these studies and not even realize that the number of people in the sample has a bearing on whether a significant relationship can be detected or not, and just accept the findings as is? Right? So if you don't know to look to see if the study is adequately powered, this might not even be an issue to the reader, but it's actually a huge issue, empirically, statistically. So it's very important to realize this. It's very important for published studies to state, we did a power analysis, so before we test our relationship, we first want to state we have enough statistical power to pick up a medium-sized effect between these variables. It's very nice when that's stated overtly in a study, especially if you're conscious that it's such a big issue. So that's just one. That's the first check of data integrity. Okay. The next check 2, are test assumptions. So, for example, in the studies we'll be looking at later on, the published studies, we are going to look at studies that use parametric testing, most often correlations, general linear models, multiple linear regression. These are the studies that assume, because they're parametric, an equivalence of variance, right? So checks that need to be done, test assumptions that need to be examined are normality, right? Are the continuous variables normally distributed? Homoscedasticity, right? Are the residuals of the dependent variable, homogeneous, similar at different levels of the independent variable? Multicollinearity, are the predictors significantly correlated? Well, not significantly, but correlated at such a high level that it's problematic, because they could be significantly correlated. They just can't be correlated at a problematic level. And we'll discuss that. And then the influence of outliers, which is a very big one, outliers being extreme scores. And then some others that we won't get into because this isn't, an illustration of test assumptions. We're just seeing if the main ones were examined. So we'll consider 2 here in this section. Consider multicollinearity and the influence of outlier scores. More specifically, how could issues related to multicollinearity and the influence of outlier scores skew the findings to our research question? Or to be more blunt, how can these issues cause our research question to be answered with errors instead of true findings? So multicollinearity occurs when 2 or more predictor variables in a multiple regression model are highly correlated. So when this occurs, findings are distorted. So typically, the findings are weakened. So for example, if you have an independent variable of interest that you want to look at in terms of the dependent variable, right, and it turns out that there's not a significant relationship between that independent variable of interest and the dependent variable, if you have other predictors that are highly correlated with that independent variable of interest, they could be causing that finding to be non-significant out of an error and not a true relationship. For example, if we were looking at how age and income impact one's level of happiness, we would need to look at our age and income, the two predictors, significantly correlated. So if we did, per se, a Pearson correlation, and the correlation coefficient was 0.8 or 0.9, that may indicate unacceptably high levels of multicollinearity. So what might this do to your findings? First of all, the age, right, the first predictor, might be significantly related to the dependent variable happiness. For example, the finding might be as age goes up, the dependent variable happiness also goes up. And there might be a true significant relationship between these two predictors. Second, there might be a significant relationship between income and happiness. For example, as income increases, one's level of happiness also increases, right? So that might be a true statistically significant finding also. So on that one-on-one level, age is related to happiness, and income is related to happiness. However, when multicollinearity occurs, the conflict, the correlation, if we describe it as a conflict between the age and income, actually makes both look as if they're not significantly related to happiness, right? So, and in reality they are, but the correlation between the two, right, the error suddenly makes it look like neither variable is significantly related to happiness. So if income was your variable of interest, but you also had age in the regression model, and then it's not significantly related, you might report there's no significant relationship between income and happiness, when truly there is, but the error caused by the multicollinearity is masking it. So our question is if the analysis indicates that there's no significant relationship, as below, between the predictors and the dependent variable, if multicollinearity is not examined and reported in the paper, how can we be sure that these findings are not due to multicollinearity? Right? So the short answer to that question, pardon me, is we cannot. Right? That's the trouble. So our next check, an outlier. An outlier is an observation that is distant from the other observations. For example, if our dependent variable is happiness and the mean score, the average score of the study participant is 3.5, which is right around the middle of the scale, right, because the range of the scale is 1 to 5, an outlier might be a score of 1, which is extremely low, extremely lower than 3.5, or extremely high, 5.0, extremely higher than 3.5. Right? They're distant from the mean score. Now, outliers, the key word here is insidious. Right? Just one outlier can really produce false findings. They can make something not, a true finding that's not significant look significant, or a true finding that is significant not look significant. So the checking for the influence of outliers in parametric testing is an absolute must. like I said, because a small number can really produce false findings. So to illustrate this, rather than just talk about it, we will consider an original valid finding, and then we'll just throw in a few outliers, and then see how that original finding is misrepresented with the addition of a few outliers. We do this to illustrate that if you do a test and you don't look for the outliers, you could just be accepting these false findings that are produced by those few outliers being present. Okay, so this is an original valid t-test, right? Meaning it was rigorously examined for all test assumptions and things of that nature. And what it indicated was that this is the SPSS statistical output. There were 47 females and 53 males, right? So you see the first blue line in the upper left-hand corner, right? 47 females, 53 males, and then to the right, the next column, the mean level of happiness for females is 3.02. The mean level of happiness for the 53 males is 2.48. So the t-test is going to tell us, is this a statistically significant difference between males and females in terms of mean score of happiness? And if you look at the bottom box, right, the lower right-hand corner, the sig, which is the probability level, is 0.000. This indicates that it's a statistically significant finding, right? So in essence, what the t-test is telling us is there's a statistically significant difference in mean levels of happiness between men and women, males and females, where females have a significantly higher mean level score relative to males. So this is our true finding. Now if we just throw in 3 outliers, see the upper left-hand corner, so now instead of 47 females, you have 50. Instead of 50 females, you have 56. We just added 3 outliers in each. So for the females, because they were the high group, we added 3 low outliers of 1.0. For the males, because they were significantly lower, we added 3 outliers of 5.0. So that this will make the mean levels more homogeneous, right, closer. So now the mean level score of females is 2.90, and the mean score of males is brought up to 2.61. Now, the interesting thing is, if you look in the lower right-hand corner, the finding is no longer statistically significant. It went from 0.001, right, to 0.09, which is greater than 0.05, which is no longer statistically significant. So if this was your first test and you did not examine, you didn't look for the 3 outliers and remove them to remove the effects of the outliers, you might accept that there's no relationship between gender and levels of happiness, which would be incorrect. The true relationship is masked by the undue influence of a few outlier scores in each group. Again, outliers can just as easily, right? So in this case, the outliers made a significant relationship look like it wasn't significant. Outliers can just as easily make a relationship that is not significant appear statistically significant, the reverse. So here's the big question we need to ask ourselves. If a researcher conducted a parametric test but didn't look for the influence of outlier scores, right? So you read a study and they don't report if they examined for outlier scores, or even worse, the researcher didn't examine for outlier scores, and then didn't report it, of course, because he didn't do it or she didn't do it. How can you be sure the findings are not based on errors related to the outlier scores? So in any study using parametric testing, if the findings are significant or aren't significant, but there's no report if outlier scores were examined or tested for, or the influence was removed and replaced, how can you be sure that the findings presented are not simply based on errors related to outlier scores? And of course, The answer is you simply can't. And that's what's so troubling about checks of data integrity, because if they're not done, if they're not reported, you really can't have a decent level of confidence in the findings, because the findings could just as easily be based on errors as not based on errors. And that's why this is so important. So recall the other test assumptions. So we just looked at multicollinearity and the influence of outlier scores. It's just two, and there's many more. So recall the other test assumptions: normality, homoscedasticity, and then the others we're not even mentioning. Each of these can easily impact the findings, making significant findings look like they're not significant, or the other way around, making findings that aren't significant look significant. So the findings are always dubious unless these checks are mentioned. These test assumptions are conducted and described. So no test assumptions equals no confidence. And then sometimes I like to think to myself, well, maybe the test assumptions are being conducted but not being reported because of lack of space in the article. But in my mind, I would posit that if you know enough to conduct these test assumptions, you also know enough that they have to be mentioned to give readers an adequate level of confidence in the findings. But that's speculative. Now here's a very interesting topic. Missing data, check number 3. This is a sprawling, far-reaching, broad topic that we're going to simplify just to illustrate how important it is. But through this one illustration, hopefully we'll show how important it is, but keep in mind, beyond this one illustration, there's just mountains of things that need to be considered and examined to look at missing data the right way. So missing data generally refers to there's no data value stored in a variable for an observation. For example, a participant might not provide a response to an item, such as income. Income is perhaps the most often skipped item. Okay, so you would say, what's your income? The study participant says, I choose not to report that, and that becomes a missing data value. Of course, there's many more, than just, missing because someone chooses not to report it. There's also not applicable, right? There's also, but we're just going to look at the first one for simplicity's sake. Now, in terms of missing data, the things to examine, how much data are missing, right? If there's one missing data point out of 100, that's a lot different if there's 20 missing data points out of 100, right? So how much data are missing is an important consideration. Are there patterns to the missingness, right? Is there a certain gender that's more likely to skip a question, or a certain racial or ethnic profile that's more likely to skip a question, right? That impacts the generalizability of the study. If there's 100 men and 100 women, and there's 50 missing data points, and it's all among the men, then the sample won't be representative of the men per se, because they're more likely to have missing data points. So that needs to be reported. And then, perhaps you can call it the big one, how are missing data treated? So once you consider how much data are missing, and you consider the patterns to the missingness, then you'd have to decide on how you're going to treat those missing data, right? And there's all sorts of solutions, from rather simple ones to complex ones with specialized software. And so here we're just going to discuss one method of how missing data are treated, not the amount or the patterns. Specifically, we will look at mean imputation, also called mean substitution, which is a very common treatment for missing data. For example, if income has a missing data value for a case, we might look at the mean level of income for all cases that did provide data and substitute the mean for the whole sample in that missing data point. On paper, it sounds logical, right? But in reality, it's very risky. And this is what we will illustrate. And so again, consider the use of this treatment method for missing income values. Let's say we have 13 study participants. Okay? Their scores right here presented for income and happiness. Right? So we have ID as the first column, income is the second column, happiness is the third column. Right now the mean level of income is 50,000. You can see it all balances out. For the first 6 scores, it's $50,000. The first ID 1 through 6, $50,000. Then 8 through 10, 3 scores of 30,000. Then 11 through 13, 3 scores of 70,000. And so it all balances out to 50,000. By the way, this is, you need an equivalence of variance, for your scores in parametric testing, which this does not really reflect. It's too homogeneous, really. But for our purposes here, we're going to use it because we can easily illustrate this missing data treatment method. So let's suppose these are the real world numbers, as in this is what exists within our sample. So if we cut it up, like I said, we have scores of happiness. So of 3.5, which is the middle of the scale, is related to $50,000. So the middle income is related to the middle score of happiness. Then in the next strata, low income, which is 30,000, is related to the lowest happiness score of 1.0. Then in the last strata, high income, $70,000, that's related to the highest happiness score of 5.0. So what does this tell us? It tells us, in reality, a higher income is associated with a higher happiness score. Right? So we have 6 study participants that have a mean income of 50,000 that have that mid-level happiness score of 3.5. 3 that make 30,000 have a mean level score of 1.0, and 3 that make 70,000 have a mean score of 5.0. Right? So as income goes up, happiness scores go up too. So this is what we know if we had complete data. However, the most likely scores to be skipped on income are people that have either really high or really low income scores. They're most likely not to provide data. So suppose that the low and high scores actually did skip the income, right? So they didn't provide a value for income. So you can see here in the bottom of the middle column, there's no reported score for income level. So what we have is empty cells, and we need to put something in there to do our analysis. So what a lot of people are tempted to do is take the mean income, which is $50,000 for all the valid cases, the 1 through 6, and enter the mean income for the missing values. So 8 through 13. So, for example, we don't know that those are the high and low scores, right? We're imagining that they just came in missing, and we don't know what they are. So the researcher may choose to enter $50,000 as the values for their income. And what does this produce? Right now, reality is hidden by these happiness scores, right? Because the happiness scores are no longer related to income. They no longer vary significantly by income. Now we have 6 study participants that make $50,000 a year that have the midpoint score of happiness, but we also have 3 study participants that also have the participants have the same level of income. So if we look at the happiness scores, those with a happiness score of 1.0, the 3 study participants with a happiness score of 1.0, they also have a mean income of $50,000. Then the mean happiness score of 5.0 on the bottom line, those 3 study participants also have a mean income of $50,000. So by imputing the mean substitution, what we've done is totally hidden the relationship between income and happiness. So if a researcher dealt with missing data points through mean substitution and didn't tell the reader in a research article, the reader would come to the conclusion that income level doesn't matter to your level of happiness, when it actually does. It was because the researcher chose to do mean substitution that made it look like it didn't relate when it actually did. And if the researcher didn't report that that was done, the reader wouldn't even have a chance to understand why these findings look the way they do. Right, so due to the choice to impute the mean to account for the missing values related to income, reality is distorted, as happiness is now equally related to low, average, and high income levels. Right? So the researcher may impute the means and not report this as a form of treatment. Again, that's an important point. It's worth saying over and over, believe me. So the big question is, if a researcher does not report how much missing data were present or how they treated the missing data, how can you, the reader, be sure that the findings are not obscured by errors related to the treatment of missing data, such as mean substitution or imputation? And of course the answer is you cannot. If missing data is not reported, how much there is, how it was dealt with, this could happen in every single study and skew all the findings exactly as we just saw. And you would have no idea. That's why it's so important to report these issues. And lastly, measurement tools. So assessing the fourth check of data integrity are measurement tools, which largely refer to examining the validity and reliability of each study measure. For example, the most commonly reported metric are ratings of internal consistency of a scale via the Cronbach's alpha, which ranges from 0 to 1. 1.0 indicating the highest level of internal consistency, 0 indicating no internal consistency. And generally it's accepted that the Cronbach's alpha must be 0.70 or greater for a scale to be reliable. So internal consistency indicates if all items measure the same or a single construct. The internal consistency examines the intercorrelations between the continuous items, and actually also you could do one for categorical items. Right? The more intercorrelated the items, the higher the Cronbach's alpha, the level of internal consistency. For example, the Cronbach's alpha examines patterns. So if we had a happiness scale and we combine these 3 items to measure happiness, there should be a correlation between items. So are you happy? If someone indicates 5, absolutely. Should be negatively correlated with are you sad? So if you say, are you happy 5, right, the next question, are you sad, would probably get a response closer to 2. And then do you feel well, right? If you said you're very happy and not at all sad, do you feel well, is probably close to a 5 also. So the stronger these types of patterns, the higher the Cronbach's alpha rating of internal consistency. So if we have findings such as this, where we say age is significantly related to happiness and income is significantly related to happiness. Right? The level of internal consistency impacts the findings, because if the level of internal consistency for the happiness scale is below 0.7, we generally assume that happiness or nothing is really being measured. So if there's significant relationships, but happiness is really not being measured, then there's actually no significant relationships because you're not measuring the construct adequately. But here's the point. The findings are described the same way. If the Cronbach's alpha is a reliable 0.90 or an unreliable 0.50, you'll still read in the research manuscript, statistical analysis indicated age and income were both related to happiness scores at a statistically significant level, right? So it sounds exactly the same, and it looks exactly the same, but in the one case where the Cronbach's alpha is 0.90, it may be a true finding because happiness is measured adequately, per se in that dimension. But if the happiness scale is 0.5, then this statement, which I said looks exactly the same, is not valid because happiness is really not being measured. So when the findings are presented, you have to know if these psychometrics are decent before you should believe the findings. Right, so the big question is, if a researcher does not report how much level of internal consistency, is evidenced by a scale, how can you be sure the constructs are not measured correctly and the findings are not reliable or credible? So, in summation, I hope we've built our case here. Checks of data integrity are necessary, right? Are necessary if one's to regard findings as credible. One mischeck can easily produce spurious findings, never mind a combination of mischecks. So the quality and the future, right? The quality and the future of statistical research hinges on making appropriate checks of data integrity. And I do not think that's too strong a statement, and hopefully the evidence that we've presented really illustrates why that's true. So we might wonder how prominent the checks of data integrity are in the literature. So now we're going to begin our examination of the 20 peer-reviewed articles to assess how the 4 checks of data integrity were assessed.